Hi all, thanks for having us. It's a pleasure to be here at CAADRIA 2021 and have the opportunity to present our work entitled Urban Design Optimization, Generative Approach Towards Urban Fabrics with Improved Transit Accessibility and Walkability. This is a work done by myself, Fernando Lima, Nathan Brown, and José Pinto Duarte at Pennsylvania State University. Our work is motivated by the fact that computational design approaches increase designers' ability to explore wider sets of potential solutions. At the same time, optimization is increasingly being used to solve complex design problems, from energy consumption to structural performance. Still, cities concentrate 55% of the world's population and are responsible for over 70% of global CO2 emissions, and fuel combustion in motor vehicles results in up to 75 urban air pollution. Besides, computational optimization techniques at the urban design scale have been limited compared to architecture due to increased complexity and computation. In this sense, we hypothesize that computational optimization can be useful in urban design when associated with generative design systems and evaluation metrics. The overall objectives are to evaluate the benefit of employing optimization tools to improve urban performance, to compare the effectiveness of various optimization algorithms for tackling problems that are recurrent in urban design, and to explore and assess different generative approaches towards the formulation of orthogonal and non-orthogonal grids from the perspective of transit accessibility. Thus, our research framework consists of combining algorithms for blocks and streets generation using physical proximity calculator for evaluating the generated fabric's performance, and also to use various grasshopper optimization plugins for guiding generation towards solution with optimized performance. Thus, in summary, we implemented a generative approach for optimizing urban fabric configuration through evaluation metrics set as fitness functions in optimization processes. Transit accessibility is a transit-oriented development principle based on locating amenities and housing around transit hubs and minimizing automobile usage, thereby contributing to more walkable and sustainable neighborhoods. Transit accessibility can be evaluated in early design by calculating physical proximity index. PPI is an index extracted from Physical Proximity Calculator, a city metrics tool developed by Lima that express on a 0 to 1 scale the smaller distance between a target and other locations in a neighborhood. The following figure illustrates the way that PPI works. In order to explore optimization possibilities in urban fabric generation, we implemented two case studies of varying complexity. For each case study, we tested several different optimization tools for a total of 168 hours of CPU processing. The first case consisted of generating uniform and non-uniform blocks using single criteria optimization for finding urban fabric arrangements with higher physical proximity indexes. The second case, in turn, consisted of addressing different approaches for modifying the best solution found in case 1, using multi-criteria optimization to deal with the transit accessibility and infrastructure costs at the same time. Case study 1 consisted of two basic parametric approaches, uniform and non-uniform block generation. In the first approach, a generative algorithm was implemented to create a rectangular grid of blocks and streets for a given area. In this experiment, all blocks had equal dimensions and four variables were optimized: block's length, block's width, street's width, and grid rotation angle. The second approach, in turn, followed the same basic structure with one crucial difference. Blocks could have different dimensions while keeping grid alignments. In both approaches, the optimization tools mentioned before were set to find fabric layouts that provided the higher physical proximity index between the neighborhood central block and all others. The goal was to identify which approach would provide better solutions and which optimization algorithm would perform better, considering solution quality and computation time. In case study 2, optimizations were performed according to the same logic as in case study 1, but with freedom beyond that of a rectilinear uniform grid. In this sense, the second case study consisted of further refining the best solution found in case 1 through three different deforming approaches for subsequent optimization. Block subdivision approach consisted of subdividing the blocks by creating new in-between street and block configurations, aiming to verify the outcomes of softening the original grid alignment. The moving corners approach, in turn, consisted of evaluating the effects of moving the block's corners while keeping the street's width, generating non-orthogonal grids. The Voronoi blocks approach consisted of extracting the original block centroids to generate a Voronoi diagram with them. Thus, the idea was to explore moving these central points and evaluating different Voronoi-shaped fabrics, defined according to the movement of original block centroids. Here we can find the case 1 approach 1 results, and here we can find case 1 approach 2 results. Note that Opossum provided the best solutions in both approaches. In sequence, we can find the best solutions through time graphs for both case 1 approaches. Case 2, in turn, provided us with the following findings. All three case 2 approaches provided better solutions than the original input in terms of PPI. As such, the optimization helped to identify that more flexible and complex grids, in terms of shape and dimensions, tend to deliver greater transit accessibility than rectangular and uniform-oriented grids. In addition, the adoption of different block patterns can lead to solutions more directed at transit accessibility or infrastructure cost, confirming the trade-off. Overall, the use of different generative approaches allowed for exploring a wide range of solutions, while multi-criteria optimization helped in identifying designs that balance transit accessibility and infrastructure cost. The Voronoi approach solutions tend to yield fabrics with less street area, and moving corner solutions returned highest physical proximity indexes. Optimization provided meaningfully better solutions than input design in both case studies, allowing us to explore a wide range of solutions according to performance metrics. Results suggest that RBF algorithm might perform better in problems structured in this way, while Cobila might perform worse. We recognize these experiments have some limitations due to urban design's complexity, multiple viewpoints, and stakeholders, since this research simplifies urban design aspects. In future works, we intend to add more complexity to the model by considering other parameters, like the location of public amenities and housing, and by adding grammar rules for topological variation, which would significantly increase the universe of possible solutions.